So thank you very much, Emperor of Regularity. Okay, so today I'm going to talk about joint work with Cristiana De Filippis from Parma and Simon Nowak from Bielefeld. So it's partial regularity, no local problems. So non-local problems are very fashionable these days. Partial regularity is much less popular these days. So I will give a brief recap on partial regularity in the local case. So in the scalar case, more or less everything is clear, and you have full regularity in the interior. This starts by the Giorgi-Nash-Moser theory, and it develops along all kinds of nonlinear settings, as pointed out since the work of Lagichinski and Durazzo. So this is the scalar case, and the information I want to emphasize is that in the scalar case, you have full regularity in the interior. Okay? So then if the boundary is regular and the boundary data are regular, then you go up to the boundary, but in the interior you have everywhere regularity. So what about the vectorial case? In the vectorial case, the situation changes, and there are two examples made simultaneously by the Giorgi and by Mazia, who show that the Giorgi-Nash-Moser theory fails in the vectorial case. So the Giorgi gave the example of a linear system like this, with with coefficients that depend only on x, but in a measurable way, where a solution develops singularities. So just the fact that the problem is vectorial gives. So the Giorgi's example is like this. So this is measurable. And so if this is not continuous, then there can be singularities. And this is just a feature of the vectorial setting. So on the other hand, if A of x is continuous, then by Starton perturbation, you do everywhere regularity. And so Mazia gave a similar example, but for a higher order equation. Then you can recast a higher order equation as a system, and the common feature is that both higher order equations and systems lack vector maximum principle. And then Giusti and Miranda eventually recooked up an example of a smooth coefficient, actually analytic coefficients, when you can plug in the solution of the Giorgi in a way that the solution makes this coefficient measurable again like this. Okay? So no way to develop, so singularity is developed in the interior. And then eventually, Natchez produced an example of an autonomous integrand, which is analytic, with discontinuous gradient. So this was the real negative solution to Hilbert's problem in the vectorial case, because there were no coefficients, no bad coefficients. Here there was just a functional depending just on the gradient. And then eventually there were this breakthrough by Zverak and Yan, who proved that there exist even unbounded minimizers, even the problem of Lipschitz discontinuous minimizer was given, and then Mooney Sabin lowered the dimension. So regularity fails everywhere. Regularity fails in every respect. So that's the thing. Then there are good references in this orange book by Giaquinta, green book by Giaquinta, and then there's an old survey I wrote in 2006 as an update to this guy. But still, you can find many references in this survey. Okay, what is partial regularity? Okay, there are irregularities, singularities. So what you do is something that started by Giusti Miranda and Morrey in the same year. Actually, both Arma and it is interesting that both Arma and Journal of Mechanical Analysis, Mathematical Mechanics were the same journal before. So that's the story that there was this Journal of Rational Mechanics and Analysis, and they split in two, and then this eventually became Indiana Journal. Okay, what they prove is that if you have this kind of systems and the coefficients are continuous, so you can prove regularity of solutions in an open subset which is full measure and actually whose complement, which is called the singular set, is a closed subset on which you can have a dimension reduction. And this is a very, let's say, semi-linear system in a way. Okay, this is in turn based on the Giorgi's work on minimal surfaces. Okay, how these things are done? What is the basic thing of partial regularity? The basic thing of partial regularity is that You start from a system, and in a small ball, you make what you do in Schauder theory. So you freeze coefficients and start making a comparison. Okay? But of course, since the coefficients are depending on the solution, you don't know if they are continuous. So you a priori impose that this quantity, which is the mean square deviation of u, is small in a small ball. This is a way to say that the oscillations are not very large on this scale. So you fix a scale and you say, okay, on that scale, the mean square deviation is small. Once this is small, you can do what you do in Schauder theory. So you make a comparison. You can do a comparison in several ways, direct, blow up, indirect, whatever you like. But this is always the same. So the idea of partial regularity is that if you have small oscillation on one scale, then this information is preserved at each scale. So, and here, so you see, this is an external information you assume a priori. Once you assume a priori this on one scale, then being a solution gives you that this is verified at every scale. And this is called excess functional. It's a way, coming back from the work of Campanato and De Giorgi, to measure oscillations using integrals, because you're only using integral estimates, and you eventually want to come up with an everywhere regularity information. Okay, so essentially, this is at the core of so-called Campanato spaces that gives you an integral way to describe Elder continuity and continuity using only integrals and not pointwise information. So this is the catch between the two things. So what you do, you freeze, and since this is by the smallness of the excess not very far from you, then the solution of this frozen problem cannot be too far from your original solution. And since this is a linear system, this one is regular because it's a Laplacian after change of scale. So on this scale, the original solution inherits the property of the linearized system and therefore is more regular. And the magic thing is that when this happens at one scale, then this reproduces at every scale, and this is so-called improvement of flatness. Improvement of flatness using minimal surfaces, using free boundaries, is always a general principle telling you that you identify a quantity which is relevant in your setting. If this quantity is small at one scale, then it gets smaller at every scale. And this is a universal principle in regularity. Okay? Whenever you're doing density estimates in scalar problems, these kinds of linearization in vectorial problems, free boundaries and whatever, whatever, it's this improvement of flatness is that if one thing is a priori small at one scale, then it gets small at every scale. Once you get this, and then you prove by this Campanato's characterization of Elder continuity, then the solution is small. Okay, that the solution is regular. Okay, the starting condition, that is the smallness of the x's, gives you the regular set. Because don't forget that you assume this at a certain point, but nobody ensures you that this is satisfied. So if this is satisfied, then you prescribe the set where this is satisfied. Since the scale is fixed, rho is fixed, this is an open subset by absolute continuity of integral, and then this gives you that this is an open subset. Moreover, by Lebesgue theory, this is satisfied at almost every point, because at almost every point, this quantity goes to zero. So you go with the information that the regular set where this is satisfied is both open and no full measure. And this is partial regularity. So once you know this, then all the rest is for free. This is open for free, and this is full measure for free, by general means. And this is in a certain sense the weakness of partial regularity, because a lot of information comes from general terms. That's why in the 70s, many people disliked partial regularity. These were all times where there were even parties. And eventually, since for Sobolev functions, the smallness of the excess comes with this Hausdorff dimension, this is also for free. Okay? This is for free. So everything is for free up to this stage. So the real core is this improvement of flatness. When you turn an information at one scale to an information at every scale. And so since you assume an information at one scale, this is an open condition, and then this is open. And then eventually you can prove this, and this is partial Elder continuity in the work of Campanato. So this is local. Everything here is local. Okay, then methods of proofs for more general systems, not only for these kinds of systems that are very special, but also for systems when the dependence on the gradient is nonlinear. So the methods of proof are blow-up methods, like Giusti and Miranda and the Giorgi from minimal surfaces, direct comparison, more in the spirit of Schauder, but the direct comparison works for a nonlinear system when you make a perturbation also with respect to the solution itself, as seen before. Then harmonic type approximation, as described by Dutzer and Steffen, this is, let's say, an interpolation between the two. So you do blow-up methods in the harmonic approximation lemma, as you see before, and then you proceed with the direct comparison after. So it's an interpolation between the two. Intermediate weak convergence methods by Evans and Hamburger. And in every case, whatever you do, you have a local linearization argument. That is, you compare the solution on a small ball to a solution of a linear problem. So you don't escape from this paradigm. Then you can do it in many ways, but this is what you're doing. So partial regularity is a local linearization theory. Okay, and then in fact, these methods are applied to more general systems like this and to more general functionals like this. The results are in these old papers, old and classical papers by Giaquinta, Modica, Ebert, Giaquinta, Giusti, Evans, Schmidt. Schmidt gave the case of non-uniformly elliptic conditions. Okay, in these cases, the excess you have to use, since you are proving that the gradient is regular, the excess you are using is the mean square deviation of the gradient. It's the mean square deviation of the gradient. So d, du, d rho x, dy, d rho x, average. This is the excess. And at this stage, you don't have a priori free estimates on the Hausdorff dimension. Okay, then there was the next basic question, is the Hausdorff dimension smaller than the ambient dimension? And does partial regularity extend to boundary? And these are further questions, because for these kinds of for these kinds of general problems, you do not have this a priori information you have for, for simpler systems, and these were open problems that then this was the stopping point of the theory until the 80s. They were the main things. So, for instance, however, we do not know if the estimates of the singular set can be improved in general, and if it's possible, improve the estimate of the singular set. I mean, these are the classical status in the 80s. So the classical status in the 80s was to find estimates for the singular sets of the Hausdorff dimension of the singular set. And this was solved in a few papers by Christensen and myself, where we proved that if you have Hilbert continuity of coefficients, something that you have to have, otherwise partial regularity doesn't hold, then you can prove, then what you know is by Gering's lemma that du is in 2 plus delta if the system has square growth condition. And then we were able to commute this delta and the Hilbert coefficients in an estimate for the singular set like this. This was done after 20 years by Christensen and myself. And this solved the first of these open problems at that time. And we were able to commute a higher integrability assumption, which is just a size information on the gradient, into an estimate for the Hausdorff dimension. And this was a bit surprising at that time, because you are commuting two things that are disconnected by themselves a priori. Ones that measure size and ones that refers to oscillations. And then the thing with, yeah? Is the Hilbert continuity with respect to the coefficients. If you are not assuming that coefficients are Hilbert continuous, partial regularity fails, by counterexamples. If coefficients are measurable, even partial regularity fails. You can have dense sets of singularities. How much? No, delta doesn't depend on alpha. How much? Delta, it depends just on the eigenvalues of the operator. This is an open problem, in fact. This is an open problem. I mean, the only result I know is due for equations is in 2 dimensions as a consequence of a deep result of a scalar. But there are no, okay, of course there are estimates on the higher integrability exponents, and it is known that if the eigenvalues go, the ratio between the eigenvalues go to plus infinity, this goes to 0, what else, of course. But there are no sharp condition on this. But what we were able to do at that time is to commute a higher integrability information into an estimate for the singular set. And this eventually opened the way to the solution to the next problem that we did with Frank. And the status at that time was that if you take a general system with smooth boundary datum and smooth boundary, even the existence of one regular point at the boundary was unknown. While it was known that even if solutions are regular up to the, if you have a smooth boundary datum and a smooth boundary, singularities can appear at the boundary. So what we were able to prove is that under optimal assumptions, because otherwise you don't even have a trace for the gradient at the boundary, almost every boundary point is regular. And this solved those problems at that time, after 20 years. Okay, then eventually, many years later, I came back to partial regularity, and we gave a description of partial regularity in terms of nonlinear potentials, because we made the bridge between nonlinear potential theory and classical geometric measure theory doing partial regularity. And among all these papers, this one is largely the deepest one. It's, let's say, in 80 pages, tour de force of technical tricks for proving partial regularities. Some kind of a monster, of a technically monster paper. I mean, with several nested, the one of De Filippis, nested with several nested exit time to avoid all kinds of things that you have in non-uniformly elliptic systems. And okay, this is as long as local partial regularity. Short from the linear potential theory, because now in the non-local case we are also using nonlinear potential theory. Okay, nonlinear potential theory is how to prove that that you have estimates. So this is a long story, started with a paper of myself and a paper with Frank that we did in the scalar case. I will only take this result, which is somehow surprising, that tells you the following thing. You have the P-Laplacian system, and then you can pointwise bound the gradient via Riesz potentials. So as a corollary, the whole theory of the P-Laplacian systems with gradient estimate is reduced to the theory of the Poisson equation. So all the papers by, let's say, all these various techniques that, by the way, only work in the scalar case by Talenti, Boccardo, Galois, Ibanez, Di Benedetto, and so forth. Now they follow, for instance, as a corollary in one shot. Because if you want to know in which space the gradient is, you just bound it by the common Riesz potential, as you do for the Laplacian. You know the mapping properties of the common Riesz potentials, and then you infer where the gradient is. In particular, on the whole Rn, you get the surprising fact that although you do not have a fundamental solution, you can bound the gradient as there was a fundamental solution exactly with the linear potential. This opened the way to several developments because, in particular, you are still using linear potentials for nonlinear problems. So, in a sense, this also, in a certain sense, it trivializes large part of the theory. Because whatever you want to do for P-Laplacian system and for quasi-linear equations, you just look at the Poisson equation, and that's the same. And although the statement is very simple, the proof is very, very long and complicated. Okay, and we also proved the following condition that will appear now in non-local problems. If you want to know a criterion that ensures that the gradient is continuous, then you prescribe that the Riesz potential goes to 0 uniformly with respect to the point. The right-hand side is a vector-valued random measure. And in particular, we prove an very old conjecture of Uraltseva, who stated that for the P-Laplacian system, the condition ensuring you that the gradient is bounded, the condition on the right-hand side, is P-independent, doesn't depend on P. And here you have that if the right-hand side belongs to the Lorentz space Ln1, then the U is continuous. In the linear case, for the Poisson equation, this is a consequence of a theorem of a well-known theorem of Stein. The surprising fact is that this extends verbatim to the nonlinear case. Okay. And now all this comes back in no-local problems, no-local case. Okay, we have a series of papers in preparation. One is already out, which is already very long, with Cristiana and Simon. And of course, the driving force was given by the young guys here. Here I'm the old guy who stays behind, who remains behind. And okay, there are papers in partial regularity by Dalir and Riviere, Shikora, very nice papers, Millot and Cyr, Roberts, Millot and Pegon and Shikora, and for specific structures, essentially for fractional harmonic maps. But we are going to do a more general case than this. So we are not confining ourselves to the general case, to a specific case where you can have more information because the case is specific, but we go to a general, where we want to, let's say, establish a general theory for partial regularity in no local problems. Okay, the system is as follows. U is vector valued. This is a tensor, and it depends in a nonlinear way by U. So this is essentially the first of the models we are considering in the first papers. Then there will be others, but today I will talk about this. And this is the non-local analog of Giusti Miranda and Morrey result. So the nonlinearity is given by this. Otherwise, you have a linear system. But we are obtaining results that are new already in the case of linear systems. Okay, ellipticity is what you know, and boundness. And of course, we also assume symmetry. This is something that can be avoided by doing some symmetrization into coefficients. It is standard, but we assume it just to be for better display the results. Okay, these are the very basic assumptions. So ellipticity and boundness of coefficients. I mean, at this stage, it's very simple. So capital N is the number of components. Okay, the right-hand side belongs to the dual of the space WS2, which is the energy space where the problem is naturally defined in. And so we are not going into the measured data setting, so the right-hand side has, at least has to belong to the dual of this space. Otherwise, we go to a different realm of problems. Okay, solutions are, as by now it is standard, contained in this space. So WS2 on omega. But then you have to prescribe a certain decay at plus infinity because you have to take into account the non-local interaction at plus infinity, so outside the domain. This is, for instance, standard when you assume a Dirichlet boundary condition. Otherwise, if you want to a local formulation, you say inside I'm WS2 and outside I decay with this speed. But there's nothing very, very strange in this fact. Just maybe this is called the tail space, but for essentially we are in WS2 inside. Okay? So this is where we are. Okay, of course we have to assume continuity with respect to coefficients as in the local case, otherwise you cannot expect partial regularity. Continuity and a certain degree of continuity. So continuity in those variables that where the solutions are, and a certain degree of also discontinuity with respect to the coefficients x and y. Because we want to incorporate we want to update the classical partial regularity theory also with the latest ingredients. Okay, the first toy model is the following result, which is essentially the fractional analog of Giusti and Miranda and Morrey theory. If A is uniformly continuous, the right-hand side belongs to L infinity, then U is C0 beta for every beta, where do you expect to be, and you have an estimate on the Hausdorff dimension of the singular. So formally, when S goes to 1, you obtain the same result, essentially the same result. So this is the expected result, and this is what we are actually, in fact, proving. And as long as the gradient is concerned, if f is in L infinity and s is larger than 1/2, this we can also drop when the right-hand side is 0, but this will be done elsewhere because there's a series of favors coming. And if alpha is less than this guy, then also the gradient is order continuous with an estimate on the Hausdorff dimension. This is what you expect. Okay, we want to consider also discontinuous coefficients, so we also considered what is known BMO coefficients and BMO coefficients. So you prescribe so what you prescribe is the integral oscillations with respect to these coefficients x and y are small if the radius is small. This is so-called small BMO condition, and when this is satisfied for every delta, this is the BMO condition. So essentially, this is a reproposition of the BMO and BMO conditions in the setting of nonlocal problems. You have to make a double integral here, but this is just a vectorial, and this is you see, independent of V and W. This must happen for every V and W. In fact, if you do not have dependence on B and W, this is the usual BMO condition. And if you are splitting coefficients, this is again the usual BMO condition. So there's no difference. All these are natural definitions. These first appeared in these works by Simon Nowak. Okay, so what we prove is that you can have partial regularity also with BMO regular coefficients. So the same thing, so we upgrade also these Giusti Miranda and Morrey results having BMO coefficients. Of course, we do not claim to do better because after 50 years, it's obviously that you can do better using other knowledge. We don't claim to be better than these people. We are saying that we are upgrading, also we are injecting all the latest novelties in regularity theory. And so this is what we are proving, again with Cristiana and Simon. So essentially, as long as U is, as long as the Hilda regularity of U, the picture is complete in this setting. But we can do more than this, because this is about just the dependence on coefficients. So if coefficients are BMO, then U is C0 beta for every beta you would expect. And this is the non-local analog of what you get in the local case. You cannot do better than this. We are still getting f in L infinity. Now we want to see the impact of the right-hand side, which is new in partial regularity, because this will be treated via nonlinear potentials. So for getting a precise description on the dependence on the right-hand side, now we are going to use nonlinear potentials. Okay, so what we found is optimal regularity, optimal partial regularity in terms of the right-hand side. If f belongs not anymore to L infinity, but to this limiting Marcinkiewicz space, then U is C0 beta, where beta is connected to the integrability of the exponent. So the idea is that if you want to have U that is in a specific beta, the right-hand side must be in this Marcinkiewicz space. This is optimal already in the case of the fractional Laplacian. You cannot do better than this. Because the scheme is the following. You have partial regularity, so you do a local linearization, and after you can do a local linearization prescribing the axis is small, then this becomes like the Laplacian, and therefore you want to use what is known for the Laplacian, for the fractional Laplacian. And as for the gradient, you get a similar result in full analogy. So this is optimal. You can look at the whole scale of optimality in this partially survey paper we wrote with Tuomo many years ago. So in the sense that you cannot do better than this. And in particular, we get the borderline regularity in terms of Lorentz spaces. If the right-hand side belongs to this limiting Lorentz space, then U is continuous. If F belongs to this limiting Lorentz space, then the U is continuous. If you look at the old papers by Talenti, for instance, this is a Talenti's condition where he proves that U is bounded when S is equal to 1. And if you go to the local case, this is our theorem with Tuomo, if for the P Laplacian. So all this range is sharp, and it is sharp also by explicit counterexamples. You can find this, I think, in the papers of Brasco and Lindgren and Shikor and so forth. And coefficients must be Dini continuous. This is also sharp. It's delicate to prove that if you want to have that the gradient is continuous, then the coefficients must be Dini continuous. This is also optimal by a counter in the local case by work of Mazia, Van Schaftingen, and Schill. I quoted yes another time. Okay, how do we prove this? Okay, this is what I was talking about. We connect these partial regularity theories with nonlinear potential theories, which is quite uncommon in partial regularity. So we introduce the so-called Harbin-Mazia-Wolff potentials, which are these objects. This is a sort of nonlinear version of these potentials that for a suitable choice of the parameters gets you the Riesz potential. And these were first used. We were first using this in nonlinear problems in an old paper by Frank and myself, where we proved this Ln1 condition and shows that the gradient is bounded. In fact, this is I think that the first paper where this Kujalceva's conjecture was set to be true. In particular, we can give a very fine description of the local Elder continuity. If this potential goes to 0 uniformly with respect to sigma, you see, if this is finite, then this goes to 0 point by absolute continuity. If it goes to 0 uniformly with respect to x, then we can prove that u is continuous. So the continuity of u is linked to the rate of this vanishing of the function of the potential, which measures in a fine way the growth of the function pointwise. So this is classical in linear potential theory from the 30s, Choquet, Brelot, Bonny, and all these people. Now this is transferred to the no-local case. That's to the nonlinear no-local case. And the same thing happens with the higher potential if you're talking about the gradient. If you're talking about the gradient, that's what you have. And these are very fine conditions with using nonlinear potentials. Once again, I think that in the local case, this was first observed in a paper by Frank and myself, right? This is for no-local systems, and it also holds for the P Laplacian system. Yeah. Look here. Omega u. This is the regular set. Of course, we first discard the singular set. Then when you are on the regular set, you are like a Laplacian, and then we can do this. This is a good remark because when there's no u dependence, then the system becomes linear with the regular coefficients. Then this implies that the singular set is empty, and this happens at every point. So what you do, you take the singular set, you throw away the singular set. So you remain with the regular set, with a candidate regular set, on which we are able to redo the same analysis that you do everywhere in the interior in the scalar case. So the approach does what it has to do. I mean, it is first you discard the singular set, and then you do the analysis on the regular set, as you were in the scalar case. Okay, and you can do more specific results concerning the existence of precise representative. Here we really reproduce the classical linear potential theory from the 30s in the no-local case. Okay, what about the technical novelties? Okay, once again, you have to introduce a tool to measure the oscillations of the solutions and to prescribe the smallness condition. Here we introduce the new notion of flatness and of excess. So this is the scalar excess. That is this one. And then in order to see what happens at infinity, we also consider the tail, which takes into account the long-range interactions. But as usual in the non-local problems, there's always a subtle interaction between long-range interactions and when you're close to the diagonal, because you never know if you are close enough to the diagonal. So you have to consider the two things separately, as we did for the first time in this paper with Cousins here. Now we do this in the vectorial case. So this is the new notion of the excess, and the smallness condition is prescribed on the whole stuff. Now there is a problem here, because while the smallness of this is given by the Lebesgue theory, now you have to check the smallness condition for these guys, which are much more complicated. And of course, this is just the excess that we use to prove Hilbert continuity of u minus the excess plus the tail, u minus the average plus the tail of u minus the average. You see, this is delicate because this is outside the ball, but this is the average inside the ball. And the catch between this and this is exactly given by the same thing. So it's more delicate than one could expect. And of course, if you want to measure the oscillations of the gradient, you do as Campanato did, you take u and you subtract an affine function. You subtract an affine function. You see, this is finite only when s is larger than 1/2. So for the gradient, you use that. So these are the two kinds of excess. Okay, a general proposition that you can prove. This holds for any function for which you belong to WS2 and the tail is finite. So this is always an open subset. So also the tail, when you move a bit the tail, this is still an open condition. So this is always an open subset. And you can have an Hausdorff dimension here. You see it's n minus 2s. S comes from WS2 because it's a general fact from fine properties that if a function belongs to WS2, then this goes to 0, n minus 2s almost everywhere. And then we have minus gamma. So we have yet an improvement that allows to say that the Hausdorff measure is 0, not only the dimension is n minus 2s. So this comes, and this tells you the following thing. For any function w and t, this is then this is true. This is a general fact that we prove. It does not only hold, so this holds for solution, this holds for general functions. If you are in TP, then you have this. And this is, let's say, the bad set. But you see, there is also a tail here. That's the point. There's also a tail. This is not only Lebesgue theory. There's this additional piece. Okay, where does this minus delta come from? Because you see, from this result, you should apply this with S and 2. But we have this minus gamma, so we have something better. This comes from this. Okay, allow me to say that it's a deep result. At least this is the most technical paper I've ever written. It's some sort of nightmare. Luckily enough, it has been checked by several people who reproduce other parts. But it's 60 pages of hard harmonic analysis. Hard harmonic analysis means that you use harmonic analysis ideas to prove a real theorem and not just abstract nonsense. And if you have, this is essentially probably one of the very few, if not the only result, which is true in the no-local case and false in the local case. And this really deserves a few words because there was a bit of misunderstanding on this. If you have a linear equation like this, then solutions, energy solutions are in W12, And any energy solution enjoys an improvement in integrability, so it's plus delta. This was proved by Myers, but Myers' proof works in the linear case because he has to do certain interpolation tricks. And then in the nonlinear case, like this, it is Gering's lemma. So Gering's lemma is for a nonlinear case. So we built an analog of Gering's lemma. But now the new ingredient is that you also improve oscillations. So you also get fractional integral, and this is false in the local case. Essentially, this is true because in order to verify a duality like this, you have to be finite against an infinite kernel. And this allows you, forces the solution to be slightly better, exactly in that range. Another proof was lately found by Shikora that uses the fact that you have solutions. We just reproduce Gering's lemma. So we state a self-improving inequality. And then O'Shea and others claim to have another easier proof, let's say 10 pages. But the point is that O'Shea's proof only works for linear things. So it was, let's say, rediscovering how to reprove Myers, while we did Gering's. So it also works for nonlinear stuff. So there was a bit of misunderstanding. Okay, but anyway, using this result, we can improve the singular set a bit more and saying that the Hausdorff dimension at n-2s is 0. And, okay, so the proposition, the general proposition is the improvement of flatness. And this is what it has to be. If you have BMO small oscillations, so if coefficients in a small ball have small oscillations, and if the right-hand side is small in a suitable scale, and this is going to build up the potential, then you have the decay of the axis. And this decays as the axis. So this is the so-called improvement of flatness. In other words, when coefficients are continuous and there's no right-hand side, you have the classical improvement of flatness. That's what you have. So, and this is the whole axis which is decaying. So the usual part plus the tail. And this is at the origin of all these statements. And okay, some notation just to tell about the techniques. I don't think I should really recover this. This is the Elder norm. This is the Gallardo norm. It's just one of the many ways you can say that a function is fractionally differentiable. And the basic tools we use is, first of all, a boundary higher differentiability integrability. So we extend this result of Cusi, myself, and Cyr up to the boundary. I mean, this is not very difficult to do. I mean, you take our proof and then but you have to do it in a way or in another because we need it. This is not a very, but it uses this deeper result of higher integrability. But it's not very difficult to translate this up to the boundary. But in a way or in another, we have to do it. Then an interesting point is a suitable formulation of this harmonic type approximation of the Giorgi. So this is a general tool that eventually Dutzer and Stefan extended to general systems with the Legendre at the mark condition that tells you the following. If you are close to be harmonic, in the sense that whenever you hit a gradient, you are very small, and if you have a bounded energy, then you can find a real harmonic map which is strongly close to L2. You see, being harmonic means that this is 0. So you say, okay, I want a degree of closeness. So I prescribe a degree of weak closeness to be. So this is a way to say, you see, that you are weakly close to a harmonic function, because the duality hitting every gradient gives you something which is small. Then take an epsilon, you can determine sigma such that if this is weakly close to be harmonic in this sense with a bounded energy, you can find the real harmonic map which is strongly close to B. This is this is how the linearization method of the Giorgi's theory minimal surface work. And what the Giorgi does is very well known. You take the minimal functional, if the excess is very small, that is, if the gradient is small, this is more or less like PD squared. And then to realize that if the gradient is small, then your solutions to this are minima to this are close to minima to this, it does exactly this. So we wanted to introduce a possible generalization of this theorem, telling you the following fact. If you assume an energy bound that involves, of course, all the actors here, that is the tail and the energy also at a higher level, but you can do it because you have higher integrability. And if you are weakly close to be let's say, an S fractional map, then you can still find a real fractional map which is close to your original solution. The point is that we, in the Giorgi's proof, this is done by contradiction. Actually, the proof is very simple. You can give it as an exercise. It's a weak convergence exercise. But it's more or less, it's better, I mean, it's the idea that counts more here. In fact, with Frank, we also cooked up a p-harmonic version of this, which is less elementary. But here, you see, you have to assume a bit more integrability, and the dependence between epsilon and this sigma 0 now is explicit, it's accepted. And we have to assume a bit more integrability, but moreover, you see, here, we take t larger than s. So this is even a stronger version, because we use a higher t is larger than s, because essentially it is not true that C0s embeds into S2. You have to improve a bit, because there's a kernel. So we describe here with this, and here this recatches up with higher integrability, so everything fits. So it's a bit more intricate than what you could expect. And this we do using certain truncation methods, truncating certain fractional sharp maximal operators. And this is a technical aspect that we have to use certain harmonic analysis tools to do certain truncations and to test and whatever. But this I would like to see a bit more. We use this Hilder truncation. So give me a W at TP function. I can find a Hilder truncation, so a real Hilder continuous function, which is exactly like this. So you see, observe that C0t does not embed here. You cannot say it because you need a bit more, but it's still both in the two. That's why I put intersection. There's some tilting due to the kernel. But so give me a fractional Sobolev function. I can find a real Hilder function such that the two coincide up to a small set that decays like lambda to the p. So once you have this lemma, then you can use this as a test function here, because you see you can only allow Hilder functions. In the classical harmonic extension lemma, you get the L infinity of the gradient. So here you should get the L infinity S0s, but actually 0t what you want to use. So you have to upgrade everything to a better level, because there's always this tilting with the exponents. And this is what you get. So we are able to, this is the way we linearize the no-local problem. So we locally linearize with the solution to the fractional Laplacian. Almost done. And okay, how do we do this truncation? We take this fractional maximal operator that extends the usual Pfeffer-Steins one. We consider the level sets of this, and then we can do some Hilder truncation. Okay, and then as a last slide, we also have a very fast reproduction of Campanato theory using this new access that we have. This uses a lot of embeddings taken by Tribes and books and blah, blah, blah. But the outcome is very simple and can be used elsewhere. because you see here we really use the x's we are using. So if you have constant coefficients, then this is smooth, and we already know it is smooth because this is fractional Laplacian. But we want to have the precise estimate to match with the partial regularity proof, and we can prove this, and then with the oscillations with the right x's, so we can combine this in the partial regularity scheme. Okay, this was the last slide. Thank you very much.